Okay, so in this flipped class video, we're going to introduce the idea of maximums, minimums, and optimization for functions of two variables. This can be done for functions with more variables as well, but it's just more complicated, and we're just going to stick to two variables for this course. So let's start off by considering a function z is equal to f of xy. Let's go ahead and get some basic definitions down. So we say f has a local maximum at some point ab if f of ab is bigger than or equal to f of xy for all points xy near ab. Now remember here, ab is a point in the xy plane. So when we say all points near ab, we mean we want to put a little circle around ab, and all of the xy's that fall in that circle are what we mean by near ab. So when we had one variable, it would have been a little interval around it. In this case, it's a little ball around it. And similarly, we can say f has a local minimum if f of ab is the smallest value for all points around ab. And finally, we say ab is a critical point if either both partial derivatives vanish there, or if one or the other of the partial derivatives is undefined. So it's not enough for one of the partial derivatives to be zero. They have to both be zero. But it is enough for one or the other of the partial derivatives to be undefined. So you should, look back at the definitions for these for the one variable case and see how similar they are. It's just we have two partial derivatives in this case instead of just one derivative. So let's go ahead and work through some examples here. So let's start with this function. F of xy is x minus 1 squared plus y minus 2 squared. So we take the partial derivatives of this, and the partial derivative with respect to x is just 2 times x minus 1. And the partial derivative with respect to y is 2 times y minus 2. Now we immediately see these partial derivatives are defined everywhere, so we're not going to have any critical points coming from points where it's undefined. So we can look for, well, where are they both 0 at? Well, f sub x is 0 when x is equal to 1, and f sub y is 0 when y is equal to 2. So the only value x and y that give both of them being 0 are when x is 1 and y is 2. So the point 1, 2 is our only critical point for f. Then we can look at the graph here and see that if we go 2 in the y direction and then 1 in the x direction, so that's going to be right around in this area here, we can see that it's a local minimum there because the graph is curving up away from that point in any direction that we go. So we get a local minimum. Let's look at this example, which is an upside down cone. So the function giving this upside down cone is negative square root of x squared plus y squared. So the derivatives are a little bit messier here. And we get the partial with respect to x is negative x over the square root of x squared plus y squared. And similarly, the partial with respect to y is negative y over square root of x squared plus y squared. So if it isn't clear to you right away where those partial derivatives are coming from, it'd be a good idea to pause the video and work those out on your own to see where the cancellations come from and where those partial derivatives are coming from. And from this, we can see at the point 0, 0, the function itself is defined because f of 0, 0 is just 0. So that point 0, 0 is in our domain for f, but we see both of our partial derivatives are undefined at 0, 0. So that means it's going to be a critical point for us. And we can see from our picture here, the point 0, 0 is the tip of that cone, so the sharp point there. And that's actually a local maximum for this function. Okay, one more example here. Let's let f of xy be x squared minus y squared. So this is pictured here with the blue graph. So if I take the partial with respect to x, I get 2x, and the partial with respect to y, I get negative 2y. So that gives me that 0, 0 is a critical point here, because both partial derivatives vanish there. In this case, it's what we call a saddle point. So it's not a local maximum or a local minimum. So our 0, 0 point is somewhere like right here. And we can see where the name saddle point comes from because it looks kind of like a saddle. But the point is if I were to walk in this direction, I would get points that are lower than the point 0. And if I walked in this direction, I get ones that are bigger than it. So it's not a local minimum because I have smaller values in this direction, not a local maximum because I have larger values in this direction. So we don't always want to have to graph the functions to figure out whether we have local maximums or local minimums. So let's go ahead and look at the second derivative test here. So in this case, we're going to have a critical point where both partial derivatives vanish. So suppose we have a and b that satisfies both partial derivatives vanish there. We're going to set d to be this value here. So you take the second derivative, second partial with respect to x, times the second partial with respect to y, and then subtract the square of the mixed partial derivative. And then we have a bunch of criteria here. So if d is bigger than 0 and the second partial derivative is bigger than 0, then we have a local minimum. If d is bigger than 0 and the second partial derivative is less than 0, then f has a local maximum. If d happens to be less than 0, we have a saddle point. And if d is equal to 0, we gain no information. So this is a lot to remember, but you can kind of think of this as similar to what we learned in Calc 1. If your second partial derivative was positive, then we had a local minimum if it was just one variable. And similarly, if the second partial was negative, then we had a local maximum if we had just one variable. So this part here is exactly like it was in Calc 1 in terms of remembering what the second partial is telling you. And then you just have to remember that we need d to be positive for either of these conditions, and then d negative gives you a saddle point. So there's more to remember, but it does follow a little bit like the Calc 1 stuff that you should remember already. So let's look at an example. So let's take this function here, f of xy is 1/2 x squared plus 3y cubed plus 9y squared minus 3xy plus 9y minus 9x. So we have the partial derivative of f with respect to x is x minus 3y minus 9, and the partial derivative with respect to y is 9y squared plus 18y minus 3x plus 9. Now both of these partial derivatives are defined everywhere, so there's not going to be any critical points coming from points where these are undefined. So we only care about critical points where both of these partial derivatives are equal to 0. So let's set each of these equations equal to 0. So we're going to take x minus 3y minus 9 is equal to 0, and 9y squared plus 18y minus 3x plus 9 is equal to 0. If we look at that first equation when we set it equal to 0, we can bring the 3y and the 9 to the other side, and we'll just have x is equal to 3y plus 9. Now what I'm going to do is I'm going to take that value for x and I'm going to plug it in here for this x here. And so I'll have 9y squared plus 18y minus 3 times 3y plus 9 is equal to 0. And now if I can factor that and get 9 times y plus 2 times y minus 1 is equal to 0. So it might be a good point here to pause the video for a minute and go ahead and work through that algebra to make sure you see where it's all coming from. But once we do that, we see, well, for this to be true, we need y to be 1 or y to be negative 2. And then if y is negative 1, we can plug it into here. And we'll get x is equal to, or if y is equal to 1, we have x is equal to 3 times 1 plus 9. So that'll give me 12. And if it's negative 2, I'm going to get 3 times negative 2, which is negative 6 plus 9. So I'll get 3. So that gives me my two critical points here of 3, negative 2, and 12, 1. So again, if you need to pause the video to work through that, please do so. So then we use our second derivative test to see what's going on here. So if we take the second partial derivative with respect to x, we just have 1. Take the second partial derivative with respect to y, and I get 18y plus 18. And then the mixed partial derivative is going to be just negative 3. So if I plug this into my formula for d of y, it's going to be 1 times 18y plus 18 minus 3 squared. So that just gives me 18y plus 9. And now I just evaluate this at my two critical points. So d of 3 negative 2 is negative 27, which is less than 0. So that tells me that 3 negative 2 gives us a saddle point. And if we look at d of 12, 1, this is 27, which is bigger than 0. So that means we're going to have a local maximum or a local minimum. And then we see our second partial with respect to x is always 1, which is positive. So that's going to give me a local maximum. Okay, so now that we know how to find local maximums and local minimums, we're going to go ahead and look at, if you recall from Calc 1, we had the extreme value theorem, which said that on any closed interval, a continuous function has an absolute maximum and an absolute minimum. So we're going to look at the same thing now, but our regions are in the xy plane, so it's a little bit more complicated. So we're going to let R be some subset. We'll refer to this as a region. And now we say f has an absolute maximum or a global maximum. Both of those terms are popular to use. On R, at some point AB, if that's the biggest value f has for all of the xy's in R. So it's not just close to AB, it's for everything in R. And similarly, absolute minimum or global minimum if it's the smallest value for all of the xy's that are in R. Since in Calc 1, we looked at closed intervals, so we need the notion of a closed region. So a closed interval meant it contained both of its endpoints. For us, we're going to say a closed region means it contains all of its boundary points. So in the interval case, we can think of the ends of the interval as our boundary points. In this case, boundary points is a little bit more general. But we can see here from our picture, since I've drawn the lines that bound this blue region as solid lines, that indicates we're keeping all of those points in our region. So this is a closed region because it contains its boundary points. Conversely, if I take this same region except for I draw dotted lines, that means I'm saying it doesn't contain those boundary points. So this is not a closed region. We also need bounded regions. So remember, we needed intervals, like regular intervals from A to B, not like from A to infinity. So the way we do that here is we say a region's bounded if I can draw a circle around it. So the circle can be really, really large, but it has to be that we can contain everything inside of a circle. So with all of that in mind, we have our extreme value theorem for functions of two variables. So we want our function to be continuous on a closed bounded region R. So think of this as just like in the Calc 1 case, except for now instead of a closed interval, it's a closed bounded region. And then we get the same conclusion that f has an absolute maximum at some point on the region, and f has an absolute minimum at some point on the region. So very similar to the Calc 1 case. So let's work through one example of this, because the boundaries are a lot more difficult to check here, because we can have some really wild shapes. So we're going to do a fairly simple one with just looking at a square, but we're going to see even just looking at a square, it's a lot more work. So let's consider this function. F of xy is x squared minus y squared. This is the one we saw earlier that looked like a saddle. And we're going to look at this on the region R given by x being between -1 and 1 and y being between -1 and 1. So if I was looking at this in three-dimensional space, this is what it would look like. Or if I just look at it in two-dimensional space, it just looks like this. Except for it would contain its boundaries because we said x is less than or equal to 1 or bigger than or equal to -1 and less than or equal to 1, and similarly for y. But for our first step here is we're going to find the critical points only on the interior. So we're going to ignore the boundary at first and look at just the points that are not in the boundary. So these are when x is strictly between -1 and 1, and y is strictly between -1 and 1. So if I take the partial derivatives, we're going to just find the critical points. So partial derivative with respect to x is 2x, partial with respect to y is -2y. So the only critical point in this region is 0, 0. And if you remember from extreme value theorem from Calc 1, we didn't have to use second derivative test to do that. We just evaluated the function on all the critical points inside the interval and at the endpoints, so at the boundary. So we evaluate our function at our critical point, and note that we just get f of 0, 0 is 0. So if you were doing this on pencil and paper, you go ahead and circle this because we're going to come back to it later. So circle that f of 0, 0 is equal to 0. And now our next step is going to be to consider what happens on our boundary. So as I said, with functions of one variable, that just meant we plugged in the endpoints of the interval and we looked at which was the biggest and which was the smallest. But we can't do that in this case because our boundary consists of 4 line segments, and each line segment has infinitely many points. So we can't just plug them all in. So you have to be a little bit more careful here. So we're going to handle each of these line segments that are on the boundary here. So like when y is equal to 1, x goes between minus 1 and 1 here. And this is when x is equal to 1 and y is between minus 1 and 1, and so on. We're going to handle each of these boundary segments separately. So let's start with the case when x is equal to 1, and we let y go between minus 1 and 1. So if we're looking at our function on that segment, we're taking x to be 1 everywhere. So our function just becomes 1 minus y squared. And now this is a function of one variable. Only y is changing here. So let's go ahead and set g of y to be 1 minus y squared. And now we're asking what are the absolute maximum and absolute minimum of this function on the interval from minus 1 less than or equal to y less than or equal to 1. Now this is a Calc 1 problem. It's finding extreme values of a function of one variable. So we go ahead and take the partial or take the derivative of this, and we get minus 2y. The only place that is either undefined or 0 is at 0 when y is equal to 0. So that gives y equals 0 as a critical number for this function of one variable. Now, of course, we have to also check the endpoints of our interval because this is a Calc 1 problem. And so we just plug all of those in. So we have f of 1, 0, because remember x is always 1 on this segment. That gives me 1. F of 1 minus 1 gives 0, and f of 1, 1 gives 0. And again, if you're doing this on pencil and paper, you'd circle all of those last 3 values because eventually we're going to look for the very biggest and very smallest ones. Now we move to the line segment when this should be line segment 2, so when x is equal to negative 1, 1 less than or equal to y less than or equal to 1. So we just run through the same thing. X is going to be negative 1 here, and just go through the exact same process. Again, we get y equals 0 as a critical number. Again, we check the endpoints, and we get these values here. Again, circle these values. We're going to come back to them. We go to line segment, which should be line segment 3, when y is equal to 1, and now we're letting x go between minus 1 and 1. So we have f of x1 is x squared minus 1. Again, this becomes a function of one variable. So we'll set h of x to be x squared minus 1 and find the absolute maximum and minimum of this function when x is between minus 1 and 1. So again, a Calc 1 problem, same steps. Critical number is only 1 is when x is equal to 0. We also check the endpoints, and we get these 3 values. And again, we circle all of these because we're going to need them in the last step. Finally, line segment should be 4. Y is equal to negative 1, and negative 1 is less than or equal to x is less than or equal to 1. And we just go through the exact same procedure. So I'm just going to skip through this because it's the same procedure. And we get these 3 values. Now, all of those values we circled, we're going to put those onto a list to determine the absolute maximum and absolute minimum. So we put all of these on our list here. And we notice the biggest possible value we got was 1, and the smallest possible value we got was negative 1. So our absolute maximum is 1, and it occurs at negative 1, 0, and 1, 0. So notice I wrote that as a plus or minus here. So when it's a negative, it's negative 1, 0. When it's plus, it's 1, 0. And then similarly, the absolute minimum occurs at 0, 1, and 0, negative 1. And let's just end with looking at a picture of what's going on here. So the minimum here is here at negative 1, 0, or over on the other side at 1, 0. 0. The y values are in this direction. So it would be at 0, x equals 0, and y is equal to plus or minus 1. And similarly, when y is equal to 0, we get x is equal to negative 1, or x is equal to positive 1 for the maximum values. So you can see it can be a bit of work to check because we had to do 4 different Calc 1 extreme value theorem problems to check the edge points of that interval. And that actually is tedious, but it was doable. Our region R isn't always going to have a nice boundary where we can just plug in and do some Calc 1 problems. So we'll see how to handle some regions with different boundaries by using Lagrange multipliers in the next section.